All right, so on the first one, again, we're supposed to find the inverse. Inverse always means to switch x and y. So this first one, instead of y equals, I'm going to have x equals. Instead of 3x, it's going to be 3y plus 1. Technically, this is the inverse, but we need to get y by itself whenever I have a function that looks like this. We're going to subtract 1 from both sides. Yep. So I'm going to have x minus 1 equals 3y. And then to get y all alone, what do I still need to do? Divide by 3. I divide by 3 over here. What do I divide by 3 on the left-hand side? Both pieces, everything. Everybody gets divided by 3. So I have y equals x over 3. How many x's are there? Just a 1x. So this is 1 over 3 x's minus 1 over 3. This is in slope-intercept form. I've got my slope, I've got my y-intercept. If you have it in slope-intercept form, what kind of a shape would it make when you graph it? A line. This is a line, which is a function. All right. Number 2, what's the first thing I need to do on this? Switch the x and the y. So I'm going to have x equals y squared. I want to get the y all alone. Right now it's y squared. How do I get rid of a squared? Square root. And if you do it to one side, have to do it to the other side. So over here, the squared and the square root cancel out. How many answers do we get when we square root something? 2. We get a positive and a negative. So I have y equals plus or minus the square root of x. If I graph both the positive and the negative of this, it's going to look like this. The positive would go like this, and the negative would go like this. Would that pass the vertical line test? If I had just the positive or just the negative, it would. But plus or minus, and it does not pass the vertical line test. This is not a function. This type of situation happens every time we do a root with an even index. So square roots, fourth roots, sixth roots, eighth roots. Anytime my index is an even number, we have this plus minus. We're going to get 2 possible outcomes, the positive and the negative. Is that true when I have an odd index? Is it true when I do a root with an odd index that I get 2 answers? No. When my index is odd, I have just 1 solution. All right, let's do this last one. First thing I need to do on this. Switch the x and the y. So x equals y to the third plus 2. I need to get the y isolated. I'm going to have to get rid of 2 things. I'm going to have to get rid of this cubed, and I'm going to have to get rid of the plus 2. Minus 2 goes first. Yes, we cancel out that 2 first. So that cancels. I have x minus 2 equals y to the third. How do I get rid of a cubed? Close, not a square root. That gets rid of a squared. Cubed root. So we're going to do a cubed root of both sides. Cubed and cubed root cancel each other out. And so I have y equals the cubed root of x minus 2. This one is a function. I don't have the plus minus on this one because it was an odd index. If it's an even index, we're going to get the plus minus, and it won't be a function. If it is an odd index, I don't have a plus minus. And so it would be a function. So far, so good?
Will we get our test back today?
Hopefully, yeah. Probably during the D-lunch time, because we're going to be running through a lot of stuff today. But I should be able to show those to you. All right. Go ahead and grab those extra notes that you picked up with the staple. The reason your bell work had inverses on it is because we are talking about an inverse today. We're talking about the inverse of exponential functions. This is what we did in Module 7. So what your test was just over. The inverse of an exponential function is called a logarithm. Logarithm.
Is that an A?
Logarithm. So it should be spelled just like this, except without the IC. Stop. Why do we have logarithms? The whole reason that we have logarithms is so we can find or solve for exponents. Yes, you may. Yep. If you want to know how to spell it, it is printed on your page. Logarithm is spelled like this. So you can copy that down. This is so that we can solve or find exponents. This is how we isolate exponents. This is how we get them alone. Up until now, when we were doing our exponential functions unit, if I had a variable in my exponent, I either had to find a way to make the bases the same, or I had to use some guess and check. Like 4 to what power gives me 16? 4 to what power gives me 64? And I had to use some guess and check there. What would happen if the exponent wasn't a whole number, though? You'd have to guess and check, guess and check. Do you guys remember when we did that on that one problem where I was like, let's see who can get the closest? And we just kept putting in exponents, and some of those exponents were really weird decimal numbers. It's the day I believe I pulled some candy out because it was lots and lots and lots of guess and check. There's a better way to solve problems like that other than just guessing and checking until you pull your hair out. And that method is what we use logarithms for. So the definition of a logarithm. We have to define it based on what we know about exponential functions. So if I have a base b to an exponent. We're going to call the exponent y. And that equals x. Then I have log. Logarithms are always written at the beginning with those three letters, log. That's how you know it's a logarithm. And then my base becomes a little number next to the g. It kind of reminds me of an exponent, except it's not up high. It's written down low. Log base b of x equals y. The base on the exponential function gets written down here. The exponent of the exponential function is isolated on this side of the equal sign all by itself. And then we call this part right here the argument. When we write a log, we read this as log base b of, and then I have my argument, equals, and the part that comes after the equal sign is my exponent. This is the only way to get an exponent isolated. And what we're going to learn how to do later on in this module is we're going to learn how to take something that looks like this and put it into the calculator so that we can find this exponent. It'll be better than just guessing and checking. All right. Domain for the parent. Is going to be 0 to infinity. For transformations, it will be h to infinity. So the parent is 0 to infinity. Transformations are h to infinity. Do you guys remember what the domain was for my exponential functions? All real numbers, and that was for all the exponential functions. It was all real numbers. Well, when I switch the x and the y, that switches my domain and my range. So for logarithmic functions, the range is going to be all real numbers. This is for all logs. What kind of an asymptote did exponential functions have? What type of asymptote did exponential functions have? How did you draw the asymptote for an exponential function? It was a line. Which way did that line go? Horizontally. If logarithms are the inverse, that means I switch the x and the y, what kind of an asymptote do you think this is going to have? This is going to be vertical. For the parent, that vertical asymptote will be x equals 0. Not a y equals, because now it's switched. We switch the x's and the y's. For transformations, This is going to be x equals, not k, because k tells me how things move up and down. What tells me left and right movements? H. This will be x equals h for my transformations.
You replace something with, you replacing 0 with h, basically for transfer.
Yes. For a parent function where h is 0, my vertical asymptote will be x is 0. If we have an h value, that will shift it to the left or to the right, and so it'll be x equals h. Yes, you may. Any questions so far? All right. I've summarized some of the big ideas here in this box. But what I really want to focus on is how to take something from exponential form and write it into logarithmic form. How to take something from logarithmic form and write it into exponential form. So I'm going to give a couple examples here, and then we're going to practice going from one form into the other form. All right. So first up, let's do 2 to the 0 power. Anything to the 0 power is what? 1. So 2 to the 0 power equals 1, right? Is that true or false? That's true. I can write that exact same idea in logarithmic form. What 3 letters did I say has to go at the beginning if you're writing something in logarithmic form? Log. The only way I know something is a logarithm is because it starts with log. What's the base on my exponential form over here? 2. Oops. So here's my base. When we're in logarithmic form, that gets written as a tiny little number low down and next to the g. Here's my base. Guys, you need to write this down. There's absolutely no way you're going to remember how to do this unless you take notes. This is brand spanking new. Where does the exponent go? So in my exponential form, the exponent is up here. In logarithmic form, where does the exponent go? After the equal sign. This is the exponent. Remember, logarithms are used to isolate exponents, to get them alone on one side. So the only thing on that side of the equal sign is the exponent. So what do I do with this 1? Where does this piece go? It's going to go after the log and after the base. It goes right here. This is called the argument. So far, so good? Right. We're going to write just a couple more things in both forms, and then we're going to practice going from one form to the other. The next one, let's do 5 to the first power. What is 5 to the first power? 5. I want to write that in its logarithmic form. So what does this have to start with if I'm writing it in logarithmic form? Log. L-O-G. What would come after that? The base. What is our base this time? 5. Over here is my base. That gets written as a little number next to the G. What do we call the piece that comes after the log and the base? The argument. What's our argument this time? 5. Here's the argument. And what goes after the equal sign? The exponent. What is the exponent on this one? 1. If you're not labeling these different pieces, I would highly recommend at least one of them get it totally labeled up so you know where all these pieces and parts are moving to. I want to do one last example like this. Let's do 4 to the negative 2. Whenever I have a negative exponent, what happens? It turns into a fraction. So this would be 1 over what? I have 4 to the negative 2. No, not 4 over 1. 16, 1 over 16, because it's 1 over 4 squared. Yes, you may. Help me write this in its log form. What does it have to start with? Log. Log. What would come after that? 4. I'm going to write something wrong, and I want you to tell me why it's wrong. Yeah, the base has to be little and next to the G. So it has to be down here. What would come after log base 4? The argument, which would be 1 over 16. And that's equal to negative 2, my exponent. Most of what we're going to practice today is just going from one form to the other. One form to the other. All right, let's look down at the bottom of the page. There are 3 examples there labeled A, B, and C. What form are all of them in?
Logarithmic.
What?
I can't say it.
Logarithmic.
You said logarithmic.
Logarithmic. There you go. Logarithmic. They're all in logarithmic form. You could also just abbreviate that and say they're all in log form. If logarithmic or logarithm is too difficult to say, everybody abbreviates this as log. How do you know when you look at it that they're all in logarithmic form? Starts with log. If it doesn't start with log, it is not in logarithmic form.
So we have to turn it into
We want to turn this into exponential form. So looking at it in logarithmic form, the first thing I need to identify is, what is the base? 4. Why? Yeah, this little guy right here is the base. Whatever the little number is my base. And that's the first thing I'm going to write down if I'm going to write it in exponential form.
And is the argument?
The argument is 64. The exponent is 3. Thank you, Hezi. So I'm going to have 4 to the 3rd power equals what? 64. Yes. Yep. If logarithmic form has an equal sign in it, exponential form is going to have an equal sign in it as well. Yes. If you put 4 to the 3rd in your calculator, is that actually 64?
Yeah.
Yes. When you write it in exponential form, it should still be a true statement. This one right here in the middle, part B. What's the first thing I write down? 3. Why? Because it's the base. We always write the base down first when we're changing it into exponential form. What's the next thing I would want in exponential form? The exponent. What is our exponent? -5. So 3 to the -5 equals what? 1/243. Could you verify that on your calculator if I asked you to?
Yes.
Yes. When you rewrite it into its exponential form, it should be a true statement that you can check on your calculator. Help me rewrite this last one. 9.
Exponent is 1/2.
Exponent is 1/2.
And is that the argument?
Yep.
Equals 3.
Equals 3. Yes. Does anybody remember what's special about fraction powers? I would absolutely get this written down on your page. Fraction exponents are roots. The index is the denominator of the fraction. We've talked about this already. We've done fraction powers and we rewrote them as radicals. That was module 6 that was full of all kinds of stuff. But we have practiced this. So if I was going to write this one as a root, what's my denominator? The index. 2. So this would be a square root. Remember, if my index is 2, I usually don't see it. So the square root, what is the square root of 9? 3. 9 to the 1/2 is the same thing as the square root of 9. Square root of 9 is equal to 3. That's what we wrote right here. I want you guys to write this one right here on the check in exponential form. I'm going to give you somewhere between 30 and 45 seconds to do that. Write the check in exponential form. Good. As soon as Jayla gets back. What does this look like in exponential form? 125 to the power of what? 1/3 equals 5. All right, flip the page over for me. We're going to go the other way. What form are all of these written in? Exponential form. How do you know? What do all of them have? They all have exponents. I know it's not logarithmic form because they don't have log. If I'm going to write this in logarithmic form, what do I have to start with? Log. What would come after that? 7. Like this? Down. Like this? Smaller. Like this. I'm going to try not to get picky about that. However, if it's full size and up on the line, just as big as you wrote log or as big as you write your other numbers, that will be wrong. Because that has a very different meaning. I'm not trying to get like pedantic or nitpicky, but if you write it the same size, it means something different. What would come after that?
17,649.
Yes. 117, comma 649 equals 6. Base goes here. This part right here goes after the log and the base. And then the piece that's all alone on one side is your exponent. What does part B have to start with? Log, L-O-G. And then what? What would I put after the L-O-G? Right after the L-O-G, what has to come next?
The base.
The base. My base is 8. Then I put what?
Oh, you put the 1 over 512.
1 over 512 equals log base 8 of 1 over 512 equals what? -3. Remember, the whole point of logarithmic form is to get my exponent on a side all alone. Help me rewrite part C. Log, small 8, 4 equals 2 over 3. Beautiful. Do the check. Again, I'm going to give you about 30, 45 seconds to write the check in logarithmic form. What does this look like? Tell me what the check looks like. Log, small 2, 512 equals 9. What's the purpose of a log again? So that we know that it's in logarithmic form, but why would we ever want to write something in logarithmic form? Yes. To get the exponent all alone. The whole point of a logarithm is to get the exponent all alone. All right. We are going to solve some logarithms. I want to know what this is equal to. So, do I know what it's equal to right now? No. So log base 5 of 25 equals, I don't know, are you guys okay if I call it y since it's an unknown thing?
Yeah. You got to figure it out.
We are going to figure it out. Can you help me rewrite this in its exponential form?
Log 5 equals 25. No.
Hold on. 5. Well, hold on. 5 to the y equals 25. Do you know what power we could take 5 to get 25? Yeah. This would be 5 to what power? Squared. So that unknown thing that we were looking for would have to be a 2. Remember, logarithms isolate my exponent. So another way I could look at this is 5 to the power of I don't know equals 25. Let's try this next one, part B. Help me rewrite this one into its exponential form. What's the base on the next log? 3. What's the exponent? I don't know. Question mark, or I could put a z there, or I could put a y. 3 to some power equals what? 27. Do you know what that exponent would need to be? 3. Because 3 to the third power equals 27. Part C here. What's my base? 7. Do I know my exponent? Nope. That's what I'm trying to find. 7 to what power gives me this argument of 1 over 7? Negative what? Negative 1. That missing exponent would be a negative 1. What about the next one? 2 to what power gives me negative what? Negative 3. That missing exponent would be a negative 3. Look at E. What's my base on part E? 9. So 9 to some power gives me 3. 1/2. Nine to the 1/2 power is the same as what? Square rooted. That's the square root. Remember, a fractional power is the same as a root. How would I figure out part F? What question could I ask myself? What's my base? For F. 32. Do I know the exponent? 32 to some power gives me what? 2.
If you were to square root it like 5 times.
So fifth root it? So fifth root of 32 equals 2. So Jaden said that would be 32 to the 1/5 power equals 2. That's absolutely correct. So this would be equal to 1/5. Take a moment to do G on your own. I want you guys to try part G on your own. Yes. Which numbers? That right there? Guess and check, honestly. So if your base is bigger than your argument, then this is going to have to be a fraction. And so then you can just start guessing and checking some things in your calculator. So 32 to the, I know I have to try a fraction. So if I try 1/2, that's not 2. 32 to the power of, let's try 1/3. It's still too big. I'm going to make my denominator bigger and bigger to make that much smaller. Okay. Does that help? Okay. So on part G, 2/16 to some power equals 6. Base is bigger than this. I know that that means the exponent must be a fraction. If the base is bigger than the argument, then the exponent has to be a fraction. So then I can grab my calculator and just start doing some guess and check with my calculator.
1/3.
1/3. On part H, what are we looking for? We're looking for the base here. What is the base on part H? Like, what do they have written for the base? B. What's the exponent on this one? 4 equals what? 81. This is my exponent. So I want you to grab a calculator, try some different bases. What to the power of 4 would give you 81? 3. 3 to the 4th power equals 81. So the base is 3. Oh, did you have your hand up? No. Okay, I'm sorry. So far, so good? All right. We're going to just begin touching on some graphing stuff. We're not actually going to graph today, but we're going to talk about graphing. Down at the bottom of the page, this is my parent function. Same exact thing as log base b to the power of x. F of x equals log base b of x. Y equals log base b of x. Shh. Stick with me, guys. We're almost done for today. The domain for the parent. Does anybody remember what we wrote down on the front page was my domain for the parent?
0 over 0 infinity.
0 to infinity, yes. What about for transformations? We wrote this down on the first page too. What is my domain for transformations?
Oh, yes.
H to infinity. What is my range for all logs? For all logs, they all have the same range. Yes, negative infinity to positive infinity. Or I can write that with that weird R symbol. All right. Asymptote. What type of asymptote does this have again? Which way does my asymptote go this time? Vertical. This is a vertical asymptote. Because it's the inverse of an exponential. My exponential functions all had horizontal. When I switch the x and the y, it switches directions. So it goes this way. What is the vertical asymptote for the parent? Vertical asymptote for the parent. This is another one that we wrote down on the front page. X equals 0 for the parent. For transformations, that would be what? X equals h. All right, last piece that we're going to add here, x-intercept for the parent. Is 1, 0.
It just rotates between 0, h, and 1.
So for exponentials, what we just took our test over, it had a y-intercept of 0, 1. This has an x-intercept of 1, 0. It's just flipped. We switch the x's and the y's. The same thing happens with my domain and range. We switch those. We use h instead of k because h tells me about left and right things. K told me about up and down things. All right, we're actually going to get into the graphing tomorrow, so we're going to stop here for today. You guys do have a short homework that's due tomorrow. It's a McGraw-Hill homework. I'm going to put those problems up on the screen. It is using the stuff that we practiced in examples 1, 2, and 3. McGraw-Hill homework due tomorrow. Problems on page 405. There are 7 problems. They're going to be fast ones like we did in examples 1, 2, and 3. So how do you write it in log form? How do you write it in exponential form? Can we evaluate these using what we did in example 3? All right? Any questions for me today? Cool.